Thanks for introduction. Well, like you said, we're going to talk about variational quantum Eigensolver today, and specifically the measurement problem that we're solving for variational quantum Eigensolver. So this won't make sense before some introduction to the basics. I'll first go through what variational quantum Eigensolver is, and then what's the measurement problem of variational quantum Eigensolver that we're trying to solve. So the outline of the talk, we'll first go through quantum chemistries, which is the motivation for using variational quantum Eigensolver. And we'll introduce some concept in linear algebra that will help us. Then we'll go into variational quantum Eigensolver, VQE, and specifically the measurement problem of VQE. Next will be some measurement optimization, which is the methods that we use to solve the measurement problems. So quantum chemistry, essentially, we're interested in some molecules, and we're interested to see how they interact with the world. So here we have H2O, and to see how it will react to the environment, there's this problem we're trying to solve called the Schrödinger equation. Here, your H is what we call the Hamiltonian. So your molecules will tell you what this Hamiltonian is, and you'll try to solve the psi and E. E is the energy of the molecules. Now, if this is not familiar, you can actually connect this to the eigenvalue problem of linear algebra. So you can see your Hamiltonian H as a d by d matrix M. You can see your psi as a d by 1 vector, and your E are just real numbers. So after all these analogy, you can rewrite your Schrödinger equation as M psi E psi, just an eigenvalue problem. So when I introduced this to my friends in CS, instantly asked, why don't you just solve it with diagonalization algorithm, which costs cubic to the dimension d. The problem is dimension d is actually exponentially large as you work with larger and larger system. So not only that you couldn't do a diagonalization, you couldn't actually list out all of these eigenvalue and eigenvectors. And that's why we'll need to solve something that's simpler. So a simpler problem, you can see that diagonalization actually solves all of these eigenvalue, eigenvector pair. But there are some physical arguments that we can make to say that we're only interested in the eigenvalues that is the lowest of all of these possible eigenvalues. What it means is instead of all of these vectors, instead of all of these eigenvalue pair, over the top, let's say we have these ED to E1 in the decreasing order, we're only interested in solving H psi 1, E1, psi 1 equation. So this will allow us to bypass diagonalization and use something we call the variational method to solve for only the last equation with the lowest eigenvalue. We call it the ground state energy. So variational method is a fairly simple idea. We have this psi wave function, or you can think of it as a vector that satisfies this, say, the norm 1 condition. So this will be connected to probability later, but let's just say this is a condition we'll work with. What you can do is this physical operation called the measurements. Your Hamiltonian comes from the molecules, and you will have some psi wave functions. And after this measurement, psi h psi will give you a particular value that's a sort of a weighted sum of your eigenvalues of your energies. Now, this is a weighted sum because of the condition that your psi transpose times psi equal to 1. And because of the p adds up to only 1, what this would then allow you to do is to write this inequality. your weighted sum of all the eigenvalues will be greater than the lowest eigenvalues. This is possible because essentially because E1 is the lowest of the bunch. So once you write the weighted sum, you automatically get this inequality. And this is useful because your E1 is something that you want, and the psi is something you can measure. So once you get psi, you can apply it onto the Hamiltonian, and you can get the value that you know has a lower bound E1. So one very simple idea came from this is that we can vary our psi however we want, as long as we satisfy the norm 1 condition. And we just do the measurements and we minimize this value over and over again. Now, there's one problem we have to address because initially I told you that psi and your H are exponentially large matrices and vector. So how do we actually deal with these exponentially large items when we want to do this measurement operation? So here we have to look at how quantum bits works and how they're different from the classical bits. I'm sure you've all heard of this explanation that classical bits can only be in either 0 or the 1 state, but your quantum bits can be in so-called superposition, somehow simultaneously in the 0 or the 1 states. Well, the nuanced answer, the nuanced explanation for qubits is actually that for single qubits, you can have this psi state where your A and B are associated to the state of being 0 or 1. And these number A and B tells you how much is your qubits in the state 0 or 1. So to make this hand-wavy explanation precise, let's look at measurements. So your single qubit in a general state is represented as A0 and B1. This is sort of like a rotating coin that measurements correspond to stopping the coin and see whether it's facing up or down. Now, once you do this measurement, there's a probability of finding your coin facing up or down, and these probabilities are related to the number A and B. So these A and B precisely tells you the probabilistic outcome of measuring your qubits. Now, to compare this to the classical bits, you can see that classical bits can only be in 0 or 1, but your qubits, in some sense, stores 2 numbers for you. But this doesn't sound very powerful because in classical computer, we can still store 2 values. What actually makes quantum computer powerful is when you use multiple qubits. So in previous case, we only have 1 qubit, so n equal to 1, and we have 2 possible states. When we have 2 qubits, we actually start having 4 states. And when we have 3 qubits, we have all the possible states from 0, 0, 0 to 1, 1, 1. So there are 8 states when we have 3 qubits. Now, if we go further, in the case when we have n qubits, we're actually having 2 to the n possible states for these n qubits, where each of them can have these coefficients, A, B, C, that represent the probability of finding these qubits in the particular state they're associated with. So this is how you see with quantum computer, you can use linear resources, so n qubits, to represent exponentially large matrices. And this is how we will use qubits to represent psi. So now we have addressed one of the exponentially large item, psi. Let's look at how we represent Hamiltonian. So I skipped through a lot of steps for this, but the Hamiltonian you will see for quantum computers are usually of this form, where you have X, Y, or Z operators, where these subscripts are telling you on which qubits they interact with. So in the basis that we see the 0, 1 state as a unit basis vector, these X, Y, Z are really just 2 by 2 matrices. So we can do a few operations to see how measurement will work with these matrices. If we measure Z with the 0 state, we will find in vector form, this is just picking out the top left elements of your Z operator. And that would be 1 in this case. So what if we use the same state to measure X? You look at the top left elements of X and 0. So these are all definite measurements. But what if you have a general wave function for qubits that has elements A and B, and you use it to measure Z? Then you can imagine that the A square elements picks up the top left 1 of Z, and the B square elements picks up the bottom right elements of Z, which is -1. So the result of this measurement will give you A square minus B square. So there's one thing we haven't addressed is how is Hamiltonian exponentially large when we're just talking about 2 by 2 matrices? Well, we'll have to look at one of the elements of the Hamiltonian. So say Z1, Z2. Z1, Z2 isn't actually just a product of 2 by 2 matrices. You couldn't use matrix multiplication to represent this relation. What you will have to do is something we call the Kronecker product. So this might seem daunting, but what you're doing is you're trying to fit the Z matrix onto each element of the other Z. So you have the Z matrix multiplying 1, Z matrix multiplying 0, and so on and so forth. What you will get out of this is a 4 by 4 matrix, where the top right and the bottom left are all 0, because at the top right and bottom left of Z matrices are 0. And on the top left is a Z matrix. On the bottom right is a -1 multiplied by the Z matrix. So you can imagine doing the same thing for n times when you have n qubits. And the result you'll get would be a exponentially large 2 to the n sized matrix. So even though our Hamiltonian is exponentially large in some sense, we can write our Hamiltonian efficiently in terms of just X or Y or Z operator multiplied with the subscript qubits. So now we see how Hamiltonians are represented and how psi are represented in qubits. We can revisit all of the ideas to get to variational quantum Eigensolver. So we have an eigenvalue problem we want to solve, but we're only interested in the equation that has the least eigenvalue. We're only interested in E1, the ground state energy. So what we do is what we call the variational methods, that you vary your psi however you want, and you get the psi value, and you minimize that to get to your ground state energy. And for psi, we're using qubits to represent this exponentially large vector. And this is essentially the idea of variational quantum Eigensolver. So variational quantum Eigensolver with this equation is written very succinctly, that you have your psi that's parameterized by theta, and you can vary this theta however you want. And what you want to do is minimizing this expression that represents measurements of your Hamiltonian. And once you have minimized it using the parameter theta, you'd hopefully get to your ground state energy, E. On a quantum computer, it'll look like this. Initially, all of your qubits are in some reference state. So say they're all in the 0 state. Then after some gates, and these gates will have to be parameterized by theta, you can prepare the psi as a function of theta. Using the psi, you can do a measurement on your Hamiltonian. And this measurement will give you a value that you want to minimize and eventually get to the ground state energy. Now, the problem arises in actually this measurement process because our Hamiltonian isn't very simple. It's some linear combination of Z, Y, X matrices. The other detail is in a quantum computer, what you're actually measuring at the end is just the Z operators. So very clearly, you see you couldn't measure the entire term of the Hamiltonian at once. And there's actually another problem, another reason why this is problematic, and it has to do with the collapse of your wave function. So we are revisiting this slide where we talk about single qubits in a general state. Now, measurements of Z correspond to checking whether this qubit is in the 0 or the 1 state. And we set that probabilistically, you will find one of the two results. Now, if you think about this, what actually happened after the measurement is you lost your information on this general psi. You no longer have access to the number A or B, and you're only left with either the 0 or the 1 state. So if you use what you're left with and then measure X or Y, what you'll get is always just 0. And that's not very useful because you've lost the information that psi encodes. So in variational quantum Eigensolver, what you'll have to do is you prepare your wave function, you measure the first term of your Hamiltonian, Z1, Z2 in this case. Then, because you have collapsed your wave function, to measure the second term, Y1, Z2, Y3, you'll have to prepare the wave function all again. So starting the process of preparing the wave function, 0, you get to the psi, and you measure the second term again. And for the rest of the 3 terms, you have to do the preparation again and again and measure each of them independently. So this is obviously a redundancy that we don't want. And this is what we call the measurement problem that we're trying to solve. So let's look at the ideal case of measurement. Say if we want to measure the Hamiltonian at once, what can we do? Your Hamiltonian, like before, will just be a linear combination of these poly matrices, X, Y, Z, with some coefficients. Now, I wrote sigma here, but sigma is just either identity or X or Y or Z. So this is what you saw before. Now for measurements, because our quantum computer can only measure the Z matrices, you'll have to find this unitary U that rotate your entire Hamiltonian into a form that consists of only the Z matrices in the middle. Now, once you have this unitary, you want to do this transformation on a classical computer. So you apply UHU to obtain this function of Z inside the bracket. And this is something you will measure on a quantum computer. On a quantum computer, you want to apply this U onto the psi wave function that you have prepared for measurements. And you can verify this equality, that because you've rotated both the operators and the wave function, this equality holds. And on a quantum computer, your procedure would look like, after the preparation of psi, you apply the unitaries and you measure these function of Z that you obtain classically. So there's a reason why we couldn't do this, and why measurement problem is something worth to solve, is once you look at the matrix representation of these Z operators in the middle, if you remember, after doing all of the connector products, you will find it in the diagonal form with only eigenvalues on the diagonal. So finding this unitary to measure all of your Hamiltonian at once is actually as difficult as solving your eigenvalue problem. And obviously we couldn't solve it, and that's why we're using VQE. So I want to ask, does anyone have questions so far? Because now we're getting to the methods. Okay, I didn't see anything, so I'll just go to the next slides. So because you couldn't measure your entire Hamiltonian at once, what you have to do in reality is you have to use the fact that your measurement is linear. So what this means is instead of measuring the entire Hamiltonian at once, what you do is you separate your Hamiltonian into individual parts. So these parts, HM. And these HM, you want them to be simple. Simple in the sense that for them, you can find these unitary, UM, to rotate HM into a function of Z operators that you could measure on quantum computer. So after you've done this, you measure HM individually, and you do this for m times because there are m parts, and you obtain the measurement of your Hamiltonian. So this is essentially what all of the measurement methods are doing. And the goal is clear, that we want this m to be as low as possible so that we don't have to repeat the preparation of your wave function multiple times. So now we'll see a few methods that address this measurement problem. So the simplest of your measurement problem is what's called the qubit-wise commuting method. So in this case, all of the term in your measurable parts would have to commute qubit-wise. So if you're not familiar with commutation, in linear algebraic term, this means that for two matrices to commute, you would have to have the two matrices to share an eigenbasis. So in our case, commute qubit-wise is something a little bit different. We're requiring on each qubit, the operator we have share an eigenbasis. And for our case, this is essentially asking all of the terms that you can measure to have only the same term, to have only one of x, y, or z. So these two terms are the simplest qubit-wise commuting terms. And they are qubit-wise commuting because on the first qubit, they both have only x1. On the second qubit, they only have y2. And on the third qubit, they only have z3. So what this would allow you to do is finding a very simple unitary to rotate both of these terms into just Z operators. What you do is you find the unitary you want that rotate X into Z. Now, because the eigenvalues of X and Z are the same, you can actually do this. The second unitary is acting on the Y2 and similarly rotating Y2 into the Z2 matrix. Now, using both of these unitary together, you can find the unitary that when you apply back to these two terms, you will just find a sum of just Z operators. And remember, Z operators is something that we can measure. So we can proceed using what we discuss, apply this unitary on the wave function, and just measure these Z1, Z2, Z3. This is This is essentially the simplest method, and we'll look at something slightly more difficult. So the more advanced method we call the fully commuting methods. And what it does is it measures a set of just commuting terms. So these sets of commuting terms is slightly different from the requirements of these terms to be qubit-wise commuting. Because you can imagine that if you commute on each qubits, then the terms that are qubit-wise commuting have to commute. But the reverse is not true. The commuting terms don't have to qubit-wise commute. And this is the simplest examples, where you have the x1, x2, and z1, z2 terms. These two terms, you may have to believe me on this, but they actually commute. And in linear algebraic terms, they share the same eigenbasis. But you can see that it doesn't satisfy the qubit-wise commuting condition, because on the first qubit, one of the terms has x1, and the other term has z1. So it's the same for the second qubit, that they do not qubit-wise commute. Now the cost of measuring all these terms, the cost of rotating them into the z operators, is that now your unitaries is slightly more complicated than the single qubit unitaries that we found. And finding these unitaries, the details of finding these unitaries actually is put in the appendix of our paper. So we won't actually go into the details of how these are done. For people with physics background, you can see this being possible because commuting in our language means these two operators are something we can measure. So this is to some extent a expected outcome. So because I won't show the details of finding this unitary, let's just look at the results. Now, I'll ask you to forget the x and y axes, because I'll talk about this in detail later. Now, the blue line is the qubit-wise commuting methods, which is the simplest method that we talked about before. And the fully commuting one is the method here. And on this plot, the lower is better, essentially. And the cost of having this better methods is that now your unitaries is slightly more complex than the qubit-wise commuting method. Now, I'll talk briefly about the Fermionic Algebra, because to go into the next method, we will have to have some backgrounds. So here you see A and A dagger. So these two sort of matrices will replace the role of X, Y, Z that you saw earlier. They're also very simple because they're working with these 0 or 1 states. But there are some details that has to do with the physics of electrons, that when they're stacked together, there are some properties which I actually won't go into. And I'll refer you to this paper by Helgeker that talks extensively on the first 2 chapters about how Fermionic algebra works. For us, I guess it's enough to just see that instead of X, Y, Z, from now on, you will see the A and A dagger operators. So here is your Hamiltonian. As promised before, instead of the X, Y, Z operator, you will find your Hamiltonian as a function of these A and A dagger operator, with a subscript telling you on which qubits it acts on, sort of. So the first term is what we usually call the one-body terms. And there are 2 subscripts, where P and Q, well, A dagger and A is like the x and y and z operators. But HPQ are just coefficients. So in some sense, you can see this HPQ as a matrix. The other term is what we call the two-body terms. This is slightly more complex than the one-body term, you can see. And the GPQRS is a tensor, or in plain terms, four-dimensional arrays of just coefficients. So this would describe your Hamiltonian, which would describe your molecules. And for measurements, instead of the Z operators that we saw earlier, what we are measuring here is the AI dagger, AI operator, where you have the same subscript on the A dagger and A. Now, we know the details of fermionic algebras, we can look at how Cartan subalgebra approach works, which is our newest method on solving the measurement problem. I'll start by saying that Cartan subalgebra approach is actually something that would apply to all sorts of algebra that you can use to describe your Hamiltonian. And fermionic algebra is just one particular algebra that we use, and we found it to be pretty effective in addressing the measurement problem. So as said before, your Hamiltonian is the sum of the one-body terms, HPQ, and the two-body terms, GPQRS. And if we recall, for the measurement problem, we want to find our Hamiltonian into a linear combination of measurable terms. Here I use the subscript m to denote the measurable terms. And on the both side, we have unitaries, just like before. In the middle, we have these AK dagger, AK, which is the thing that you can measure on quantum computers. So you can see all of these ideas is exactly the same, that you want your measurable parts at the middle, and then let's calculate expectation. Okay, so the last slide, this is just addressing that instead of the Z operators that you measure on a quantum computer, in this algebra, what you can measure are these A dagger A with the same subscript I. Does that answer your question? Thanks. Feel free to interrupt me if anything doesn't make sense. Actually, it turns out that I can see the chat pretty well, so notify me anytime. So the idea here is the same for measurements, even though we're working with different algebra, that on both sides, we want to apply this unitary operator. And in the middle, we have these AK dagger AK, which is something that we can measure on a quantum computer. So there's one problem that we have to address, that now we have written down this form for measurements. How do we actually solve it? Because there are two unknowns here. CK is unknown, and the lambda TU is unknown. And the third unknown is actually the number of m, so you're not sure how many individual parts that you want to write your Hamiltonian in. So there are multiple methods, actually two methods that solve it, and we'll talk about how to deal with the one-body terms. So the one-body terms is this HPQ element, and because of the isomorphism or the correspondence between these AP dagger AQ to matrices, what you can actually do is you can see HPQ as a n by n matrix to diagonalize. So here we're seeing a diagonalization using subscripts. And this what tells us, diagonalizing H, what tells us the unitary, the UPK matrix that would in turn allow us to find the unitary operator that we need to apply to the one-body terms. This is, again, this is like having your measurable parts at the middle and the unitaries dressing on both sides. So what turns out is the entire one-body terms is measurable at once, because now everything is just AK, dagger, AK, after applying single unitary. And this is nice idea that we got from our competitors, from Google and the Berkeley team. Now, they're also addressing the measurement problem in the Fermionic Algebra, but our methods and their methods are different in how we deal with the two-body terms. So I won't get into how they deal with the two-body terms, but I will go on and talk about the Cartan subalgebra and how we deal with the two-body terms. So the one-body terms are dealt with, and our Hamiltonian consists of only these two-body terms with GPQRS tensors. Following the same idea, we want to write it as a form that we can measure. So here, what I've done is I've expanded the lambda LK into a tensor form with the indices LLKK being non-zero. And writing it this way is allowing us to, again, use linear algebra to solve the problem, to solve this decomposition. So there's a way to get rid of all of these operators, again, because of the correspondence between A dagger and A to matrices. We can write down this sort of a tensor decomposition for four-dimensional array, GPQRS. And you can see the similarity of this to the diagonalization, because on the left-hand side, you have a general tensor, four modes tensor. And on the right-hand side, you have the lambda tensor that is diagonal in a very specific sense, because on the first two indices, it's diagonal, and the second two indices, it's diagonal again. And the unitary, usually in diagonalization, we have a single unitary and apply once on the left, apply the other time on the right. Here, because we have four modes, our unitaries apply twice in a sense. And from here, you can probably see the connection of this to diagonalization. Well, what turns out is this is a special enough decomposition that we couldn't find any existing algorithm that just solves it online. So what we do is we have a hyperparameter M that we have to choose beforehand. And once we choose the hyperparameters, we parameterize these lambda LK that are unknowns, and we parameterize the unitary UQL with some angles representing your unitary matrix. Now, our algorithm will have lambda and U as parameters, and for them, we can get the gradients. And with gradients, we can solve this equality using gradient descent. So that was all of the methods, and we can look at results now. On the x-axis that I didn't explain is, if you remember, your Hamiltonian is a linear combination of these poly P. Pauli matrices. So X, Y, or Z that you saw earlier. And the number of these X, Y, and Z that you need to represent your Hamiltonian is plotted on the x-axis here. So K is shown on your x-axis. On the y-axis, for all of these measurement methods, we're separating the Hamiltonian into measurable parts. So we're writing our H into sum of HM, where each of the HM are measurable. On the y-axis, we're plotting this M, which is the number of groups that we're measuring. So the first line, you see, the blue line, I'm just plotting the y equal to x, the y equal to x line that represents sort of the original problem, the original difficulty that you got from your molecules. On the yellow line, this is the qubit-wise commuting methods that we covered. And you can see the n to the 4 represent the scaling with respect to the number of qubits. And qubit-wise commuting method doesn't actually reduce the scaling of the original problem, because somewhat expected that qubit-wise commuting is a very strict constraint. So isn't actually very effective for reducing scaling. A slightly more complex method is the fully commuting one. And in the blue line, in the green line, they can see it reduced the scaling by a linear term. Now, the method that I skipped, which is developed by our competitors from Google and Berkeley, they managed to reduce this to n-square scaling. And finally, our Cartan Subalgebra approach, which I should specify that this is Cartan Subalgebra approach acting on the Fermionic Algebra that has the scaling n to the 1.4. That is actually, as far as we know, the most efficient methods in terms of numbers of grouping. So let's talk about the future research, because as you can see, Cartan Subalgebra actually has a lot of future directions to go. So first, I've talked about this before, that Cartan Subalgebra is something that's flexible, that you can apply on multiple algebras that you may wish to use to represent your Hamiltonian. And for us, we only tried Cartan Subalgebra in the Qubit algebra, so the XYZ algebra, or in the Fermionic algebra with A and A dagger. It's interesting, and I think some people are working on it, is applying our Cartan Subalgebra approach to different algebra, like SO2N. The other thing is, if you remember a few slides ago, we were solving a diagonalization like tensor decomposition. And you might be, like me, quite unsatisfied with the way we dealt with things, because for one, we are relying on optimization. So there's a problem of the starting points. You can potentially use some heuristics to find a good starting point that will allow your gradient descent algorithm to converge to an optimal solutions. So that's one direction. The other is we're using gradient descent, and specifically, let's see. So we're using a particular optimizer that uses gradient descent, but potentially because of the structure of the problem, there may be other optimizer that are more suitable for solving this tensor decomposition. And this is just something that we haven't looked at. The other thing is from Hamiltonian, because it's a physical thing representing a molecules. You might expect some obvious structure for you to exploit that potentially you can solve this tensor decomposition just directly without any optimization. And although as a general mathematical problem, we didn't find this tensor decomposition to be possible, it's likely that because we're working with molecules, our problem is slightly easier than just a general mathematical decomposition. And I'm talking about all of these future directions because, as you can see, we're only working with linear algebra most of the time, or sometimes we're working with tensors that has that really just multiple dimensional array. So maybe if you're from CS or engineering and who haven't looked at quantum mechanics, you shouldn't be scared because all of these things, as you can see, just relies on linear algebra. So once you understand linear algebra, you're good for research in this field, and we welcome you to apply to our group. This is the recognition. If you want to come to our group, you want to contact Professor Arthur Ismailov. He's a professor, so you should talk to him about your backgrounds and your interests. Now I want to thank Robert Lang and Manuel Diaz-Tinoco for multiple discussions on all of these things that we work on. And if you're coming to our group, everyone is nice and smart. I think you'll have a really good time here. So this is the Arthur Ismailov group. Professor Ismailov is the leader.
All right, thank you so much for the talk. I also congratulate everybody for I guess conquering this highly technical talk. I know probably for some first year maybe the information is dense, so congratulate you for sure. So yeah, the little plug at the end, that's definitely welcome. Actually, I think I noticed Professor Ismailov is actually in the chat, so I guess maybe I'm not encouraging to send a DM, but maybe something you can do there. But yeah. Okay, so we're gonna start our Q&A session. So any questions you have for Thompson's? I know I think there was a question in the Q&A about theta and phi. So I think that was perhaps due to some confusions on perhaps when we were talking about using the unitary matrix to transform the Hamiltonian. Maybe there's some questions for clarifications there.
Okay. So I missed this because this is in Q&A, but let's see. So this is at the VQE slide, I believe. Right?
Yeah, I think Ernest can probably chip in. Also,
you can actually. Sorry.
Yeah, sorry. I was just gonna say, if you guys want to just be unmuted to talk, and that's okay too. I can unmute you if you just raise your hand. Okay.
I mean, I think you can think of them as phases because at the end of the day, these are parameters for your quantum gates. And quantum gates usually are exponentials to some operator. And you can think of them in phases in that sense. But it doesn't really matter to talk about them as angles because they are just parameters.
Okay.
That parameterize your wave function.
So they're more like phases, right?
Essentially, yeah, sure.
Yeah, okay. That's what I wanted to clarify. Thank you.
Hey, Thompson, I have a question.
Sure.
So you mentioned, your Cartan algebra method over different algebras.
Mm-hmm.
So, to my knowledge, this Cartan subalgebra, it's something you can define for basically any simple Lie group, right? That's not one of the exceptional Lie groups. Is there a reason to believe that there would be barriers in extending it to other algebras?
So there's one thing that's interesting that we call, there's one algebra SO2N, and in terms of operator, it's Majorana operators. And they're interesting because it's sort of the in-between of Fermionic algebras and the Qubit algebras. So the idea is going from Fermionic algebra to Qubit algebras, you're doing some kind of Barbie-Kataf or some sort of transformations. And as I'm told, Majorana operators is actually one-to-one to these qubit operators in the same mapping. So essentially, they are. You can first go to the Fermionic. You can first go to the Majorana operators, and then one by one go to the Pauli operators. And there are some results using Majorana operators for VQE. So that's actually one of the interesting things to look at when we're talking about other algebras to apply CSA.
Thanks.
Oh, I noticed Ernest lowered his hand and then raised again. Is there other questions?
Ernest, you can just type on the chat. I can see, and or you can just talk.
Oh, I have permission. My bad. So when you take this measurement, I mean, you're looking usually at some kind of orthogonal measurement that will then collapse the wave function for a particular qubit, right? Or at least
Sure.
Can you just comment on if it doesn't affect the parameters of the system or the state of the rest of like the quantum computer per se, is this okay or not?
You're asking why collapsing the wave function is bad for our purpose?
Well, I mean, if it doesn't affect the other parameters of the system or other qubits, then it's not so bad. That's what I'm kind of asking.
Okay, so with this example, you're trying to measure this entire Hamiltonian with some z and y and x, right? And say you measure z1 for the z1, z2 operator. You collapse the wave functions, and for the first qubits, you will always have either the 0 or the 1 state. And this is bad because after the collapse, when you go again and measure your y1, you will always have the 0 or 1 results, the 0 results actually. So it doesn't affect your parameter, yes, but after the measurements, you would lose the information inside that you want to achieve by parameterizing your wave function.
Okay, and that's because it has the Z2, right?
Because so in this case, it's because it has the Z1 and there's a Y1. So after you measure Z1, you wouldn't be able to measure the Y1 of the second term.
Okay, yeah, because you can't, that qubit has collapsed. Okay, gotcha.
Right,
Thank you.
right, yeah. So essentially, that's why you have to do the preparation again for the second term. And you want to do this as little time as possible.
Okay, is there any other questions from the audience? Okay, if not, then thank you so much for everybody who showed up. Thank you so much for Thompson for giving this talk and putting all these slides together. They're very dense with information and definitely interesting, at least in my perspective. Thank you so much for your hard work, and also thank you for everybody who showed up and contributed to the discussions, and we loved your participations. We have one last event or one last talk in our talk series that will be happening on Thursday. So it's DHA talking about quantum, different quantum computing structures again, architecture again. So we're looking forward to see all of you there again. But yeah, so thank you so much. Yes, that's the continuations of last time because we sort of ran over time there. But yeah, so thank you so much and have a wonderful evening. So I will end our sections right now.